Welcome all of you. So we have already completed the introduction part where we went through different basic concepts, energy scenario, Sankey diagram, and capacity factor and load factor. And now coming to the actual part of the course, renewable energy sources. So the first renewable energy source that we will be looking at in detail is solar energy. So in today's lecture, we will study about sun and solar energy. What is sun? What are the properties? What type of radiations that we receive? What is the composition of radiations? Solar constant and the concept of air mass. So sun, it is the largest object in our solar system, and our solar system accounts of sun and I think 8 or 9 planets. I think Pluto is not considered as a planet. So right now we have 8 planets moving around the sun in elliptical orbits, and then there are so many asteroids and comets which accounts for the entire solar system. So of that solar system, of all the objects in the solar system, it's the sun which occupies or accounts for 99.86% of the total mass. So it means this entire solar system is obviously about sun, and it's much bigger than all the planets, each of the planets in the system. And solar energy, it is the radiant light and heat energy which comes from the sun, and it is this radiant heat and light which can be captured and converted into useful energy with respect to earth. The characteristics of sun, it's it's a sphere made of like gases, and it has mass in range of 10 to the power 30 kg. Diameter is also like 1.3 million kilometers, and the temperature of the surface, it's 5700 Kelvin, and pressure is 0.0008 bar. But at the core, temperature and pressure had been million Kelvin and billion bar, and that's what we had studied earlier also. It is at this high temperature and pressure we have the reaction of nuclear fusion. This high energy, like high temperature and pressure, it makes hydrogen atoms to come apart, and their nuclei fuse together to form a helium atom. So 4 nuclei of hydrogen atom combine together to form one helium atom, and the mass of this formed helium atom is always less than mass of 4 hydrogen nuclei, and this difference in mass is emitted as energy, and that's what is nuclear fusion. So the solar radiation, it is the electromagnetic energy emitted by the sun, created by nuclear fusion reactions which occur at its core, and it is this energy which travels through space and reaches the earth in the form of heat and light, and this energy drives our planet's climate, weather patterns, and life sustaining processes. If you remember the picture which I showed in lecture 1, where sun is responsible for directly or indirectly all other sources of energy on earth, with some exceptions of nuclear and geothermal, it tells us like how all the life sustaining processes are survived or are sustained because of the energy offered by sun. Photosynthesis, for that we need sunlight. Okay, formation of like growth of biomass, fossil fuels, changes in wind patterns, weather patterns, hydro, wind, solar. So all these are coming directly or indirectly from sun. The radiation or solar radiation, the units or the terminologies depend on like whether we are measuring it instantaneously or for a period of time. So when we talk about instantaneous intensity of solar radiation hitting on a particular surface, the term is called irradiance. It tells us the power, watt per meter square. Okay, this is instantaneous, so maybe for a second. And when we talk about energy in kilowatt hour per meter square, it tells us the accumulated amount of or the collected amount of solar radiation on an area received over a specific period of time, and the term is called as insolation. Insolation term, it's actually made from the initials of 3 terms, which is incident solar radiation. So you get insolation. That's how that term is formed. But often in numericals or in our daily lives, we will treat these terms as just radiation. Many times you will just find that solar radiation of this type is 100 watt per meter square or 200 watt per meter square. So, radiation is also a commonly used term in place of irradiance or insolation. Let us look at availability of solar energy. So, all the energy which is coming from sun, if we give it a value say 100%, how much of it is actually making its way to the earth? So, most of it is reflected. So, almost 30% is reflected from the atmosphere by the clouds or from the earth's surface. Okay, and 51% is absorbed by lands and oceans. Now, whatever is absorbed by lands and oceans or small amount of energy is absorbed by atmosphere or clouds, total of this energy is later re-radiated back to space, and that is what completes the energy balance. If we look at 100% incoming energy, almost 100% goes back to the atmosphere. This is 624, that is 30, and this is 70. So, almost 100% goes back to the atmosphere later. But during the time when this energy is absorbed by lands and oceans or other parts of the atmosphere, it is a portion of it is used for sustaining life processes on earth. So, amount wise, the total solar energy which is absorbed by earth's atmosphere, ocean and land masses is around 3.8 million exajoule per year. Exajoule is 10 to the power 18. That is a huge amount of energy which is absorbed by earth. And energy use or energy demand for human beings per year is just 550 exajoule. It is not even 0.01% of the total annual energy that is coming from the sun on the earth. And if you look at this matrix, it can help us understand, like, even though solar PV or solar thermal have like say low efficiencies, but if we are able to maximize the capture of solar energy to satisfy our energy needs, we have plenty of it. It is a huge abundance of available solar energy compared to what is actually required, and that's one of the reason why the investment and the technology and R&D in solar sector has gone has been exponential. The growth or the rise of all these investments in the solar sector has been exponential. Now, if you look at the spectrum of solar radiation, what type of radiations they are composed of? So, it is mainly three types: ultraviolet, visible and infrared, based on the spectrum. And you can see from this graph also, infrared radiation makes up to 49 to 50%, visible light 42 to 43%, and ultraviolet radiation makes up 7 to 8%. The red pictures which we are seeing here, this is a graph of irradiance versus wavelength, and each of these three types of radiations have different range of wavelengths, and that's how these graphs are marked. Okay. Now, in infrared radiation or in visible light, this is the yellow part shows the sunlight without atmospheric absorption, and the red one shows the sunlight at sea level. So, this water vapor, oxygen, ozone, CO2, these are the greenhouse gases, and they mainly try to absorb the radiation, and that radiation is infrared radiation. You might have heard that UV is not good for human health. Wherever we have holes in the ozone layer, it's because of UV people are getting skin diseases, skin cancer, skin burns. Okay, so yeah, UV is harmful, but if you talk about global warming, it's not because of UV or visible light, but mainly the infrared radiations, because it is this radiation which is absorbed primarily by greenhouse gases. And when this radiation is absorbed by GHGs, with the increasing concentration of GHGs in atmosphere because of anthropogenic activities, it has led to rise in global warming. So, out of all these three radiations, it is the infrared radiation which leads to global warming. Now, with that background of sun and solar energy and composition of radiation, let us look at the first concept, that is solar constant. So, if with respect to sun, if Earth is at some distance, and the maximum energy which is received by from Sun to Earth, this is going to be maximum right at this point before the atmosphere of the Earth starts, actually at the surface of the Earth just outside the atmosphere, and it is this value which is called as solar constant. It is a total energy received from the Sun per unit time on a unit surface area, which is perpendicular to the radiation in space just outside the Earth's atmosphere. Okay, so at this point, or at this point which is say perpendicular to the Sun's radiation, we get the maximum radiation, and this happens when the Earth is at its mean distance from the Sun. So if this is Sun with radius r, Earth has its own radius, and let r be the mean distance from the center of Earth to the center of the Sun. Earth keeps on revolving around Sun, it also keeps on rotating around itself. So for the solar constant, we are just interested in the mean distance between Earth and Sun's distance. Now, how do we derive this value? So we know that Earth moves around the Sun in the elliptical orbit, but for deriving the value of solar constant, we make an assumption that Earth is moving in a circular path of radius r with Sun as its center. So this radius r is nothing but the mean distance between Sun and Earth. So let's assume that Earth is moving around Sun in circular path. Now the second assumption here is Sun is a perfectly black body, so that the energy which is radiated from Sun per unit time from the surface of the Sun as per Stephen-Boltzmann law. What is Stephen-Boltzmann law? The heat transfer flux because of radiation, it is proportional to the surface area, and it is also proportional to the fourth power of the temperature of the surface or temperature of the source, and the constant of that proportionality is called as Stephen-Boltzmann constant. So the energy radiated per unit time will be H equal to A sigma T to the power 4, where A is the area, surface area of the Sun, T is its absolute temperature of the surface, and sigma is the Stephen-Boltzmann constant, which has a fixed universal value. So till this point is clear. What we did, and the derivation starts with the assumption that Earth is moving in a circular orbit with the radius equal to mean distance, that is small r. Sun is a perfectly black body, so if we apply Stephen-Boltzmann's law, the energy radiated is given as H equal to A sigma T to the power 4. Now how much energy is actually received by, this is the energy given by the Sun. Now how much is the energy received by the Earth? That's what we need to calculate. So since Sun is a sphere, the area of the sphere is 4 pi r square, where r is the radius of the Sun. So we can write it just 4 pi r square sigma T to the power 4. Now by the time this power which is emitted by Sun, it reaches Earth, it is spread across a sphere with a radius equal to the Earth and Sun's mean distance r. So while it is spread over all this distance, the energy received by Earth's per unit area per second would be whatever energy is transferred upon the sphere with the radius r, that is 4 by r square. H value is given to us 4 pi r square sigma T to the power 4. Now this 4 pi can be strike off. What we would get is r upon r square sigma T to the power 4. Now in this, where S is the energy received by Earth's unit area per second, and this is what is solar constant also. So r, that is radius of Sun, small r mean distance, sigma Stephen-Boltzmann constant, and T is the temperature. All four are universally known quantities. If you substitute these numbers in this formula, you should be able to get the value of solar constant as 1366 or 1367 watt per meter square. Okay, depending on, because certain books refer to 5778 Kelvin or 5777 Kelvin. it may change slightly, but it will be within this range only. It will be between 1361 to 1369 for sure. Now, that is the value of solar constant. So, at a point just outside the Earth's atmosphere, since Earth is called as terrestrial territory, this can be called as extraterrestrial point or extraterrestrial radiation. The radiation received at this point is called as solar constant. But now, coming back to the reality, which tells us Earth's orbit is elliptical around the sun and not circular. So, this if Earth is moving around the sun in this elliptical orbit, it varies by plus minus 3% within the same value. Okay, and this radiation, like I told you earlier, solar radiation incident just outside the Earth's atmosphere is called extraterrestrial radiation, and it is the radiation striking the surface of Earth, assuming that there is no atmosphere. Suppose you assume that there is no atmosphere, so whatever point we are talking at the surface of Earth outside the atmosphere, the same amount of radiation would strike the surface of Earth. And solar constant is nothing but the average value of this extraterrestrial radiation. And if you account for that plus minus 3% with the time of the year, the solar constant or solar irradiance varies from 1400, I guess 20 something to 1321. Okay, so that's a range within which solar constant can vary or extraterrestrial radiation can vary, and the average of this comes out to be the solar constant, that is 1367. The second concept that we have to cover today is air mass. So, solar constant, it gave us the maximum solar radiation which can reach at a point just outside the Earth's atmosphere or Earth's, if we assume atmosphere as part of Earth, so that is the Earth's surface. Now, air mass, it tells us it is a parameter which determines the solar irradiance under clear sky. Okay, and it is the distance that sunlight has to travel through the atmosphere. So, if sun is here and radiation has to travel through the atmosphere, so this proportion, this distance is actually the parameter determining the air mass. The ratio of actual path of sunlight, so this is the actual path of sunlight to the minimal distance, it's known as the air mass. Minimal distance will be at the zenith point or the noon point. So, air mass represents the portion of atmosphere that the light has to pass through before striking the Earth related to its overhead path length and is equal to y by x. So, when sun is at the zenith position or the noon position, angle z or theta z is equal to 0. Now, if sun is at some position, let us say here, and the distance is y, so the angle measured from the vertical is called zenith angle. So, the air mass is defined as actual length, that is y, by the shortest length, that is x. So, this can be derived by the cosine of this angle. So, if I just calculate cos z, it will be, it is a right angle triangle here. So, we can apply trigonometry. Cos z is equal to adjacent side by hypotenuse. So, 1 by cos z will be y by x. So, y by x is our air mass. So, 1 by cos z is the air mass. So, if we know the angle from the vertical, if we know the zenith angle, that which tells us the position of the sun with respect to the vertical, we can calculate the air mass. Now, there is another way to calculate air mass. So, when the sun is at zenith, optical air mass will be unity because cos 0 is 1. So, 1 by 1 would be 1. So, air mass will be 1 when the sun is at its zenith, the topmost position, the overhead position. And air mass is commonly used to characterize the performance of solar cells under standardized conditions. If you take any solar cell, the real solar cell, there you will see some specifications mentioned there. the radiation, it would be 1000 watt per meter square, tested for that. Then air mass, it will say 1, 1.5 or air mass 2, some kind of specifications in terms of air mass would be there. Another method, if you don't know the zenith angle, the easy method using Pythagoras theorem. So if we have an object or a pole of height h, and if sun is behind that pole, so it will have some shadow, and if we calculate the length of the shadow, based on that we can calculate the air mass. Air mass is 1 plus s by h square. So if we know s, if we know h, we can calculate the air mass just by using the Pythagoras theorem, which is this value. Now, above expressions, both the zenith angle one and this Pythagoras theorem one, they assume that the atmosphere is a flat horizontal layer, but in reality earth is not flat, earth is not horizontal, it is a spherical in shape. So with respect to the sun's position, the surface of the earth is like a curvature and not a flat horizontal layer. So a lot of researchers have done, have come up with some correlations to account for the curvature of the atmosphere, and in that it was observed that air mass is not quite equal to the atmospheric path length. Whenever the sun is close to the horizon, it is not equal to the path length. So one such equation is given by Kasten and Young in 1989, where you can see it's 1 upon cos z plus some zenith angle based mathematical correlation which takes into account the curvature of the earth's atmosphere. But commonly we use those simple approaches because for most of the angles, like at least till 75 degree, the values given by both approaches is almost similar. Only at very high zenith angles, like when sun is like almost towards, like very close to sunrise or sunset, where we won't be much interested in tapping the radiations. At that point, like after 85 degree, there is a huge variation between the two approaches, but for the majority of the time when we are most concerned about the radiations, it gives us the similar values. So that's why for both for air mass we can use the approximate formula. Let's take one numerical before we close this lecture. So we have studied the concept of solar constant and air mass. Now extraterrestrial radiation for solar irradiance or solar constant is 1367. It's a universally known value. At a air mass of 2, if atmosphere is able to transmit only 70% of that radiation. So if this is, and this is the atmosphere just at the surface, let me make it a little bigger. So at this point we have the radiation as 1367. Now when it passes through the atmosphere, and that aerial atmosphere, it governs the property of air mass. So if air mass is 2, only 70% of the radiation is able to reach the earth's like land surface. Now what I have to calculate? Calculate the solar irradiance reaching the earth's surface, that means the land, and the corresponding zenith angle. So let's see. So obviously for air mass we will be needing zenith angle, or for zenith angle we need air mass. It is given to us, so we should be able to calculate from 1 by cos z. Given data is solar constant 1367, transmission 70%. So solar irradiance reaching the earth's surface would be 70% of 1367, right? It comes out to be 957 watt per meter square. And for zenith angle, what we need is air mass. Air mass equal to 1 upon cos zenith angle. So for air mass 2, it will be 1 by cos z, or cos z is equal to 1 by 2. It is represented as z or theta z, okay. So cos inverse of 1 by 2 is 60 degree. So that's the zenith angle for this given numerical. So if we know the air mass, we can calculate zenith angle, and the vice versa. If we know zenith angle, we can calculate air mass. And from the transmission and solar constant, we are able to calculate the actual solar irradiance which made its way to the surface of the earth. So with that, I think we can close today's lecture. Just to summarize, we started with sun, how it constitutes major portion of the mass of solar system, and what are its like key parameters like pressure, temperature, diameter, mass, and it clearly shows that it is significantly huge than any of the planets in the solar system. Then we looked at solar energy or solar radiation. What's the composition of solar radiation in terms of UV, visible, and infrared. And we also discussed how infrared radiation is the one which is responsible for greenhouse gases, or which can be absorbed by the greenhouse gases, and then which is responsible for global warming or climate change. Then the next concept we studied was of solar constant. It tells us the maximum amount of radiation that can reach on the Earth's surface right at a point just outside the atmosphere. Okay. Or it can be also defined as the extraterrestrial radiation, or the average value of the extraterrestrial radiation with respect to Earth, and that number comes out to be 1367 watt per meter square. We looked at the derivation, how to get this value using Stephen-Boltzmann's law, and the swept area in the form of sphere with respect to Earth and Sun mean distance, right? But then in the assumption we had made circular orbit. If we take into account elliptical orbit, it varies by plus minus 3%, right? And that's what we saw, the variation of solar constant over a period of year, and it's a cyclic variation. Okay. And then finally we looked at the concept of air mass, which tells us the distance through the atmosphere, like the distance traveled by the sun rays through the atmosphere before it made its way to the surface of the Earth, and it is given by like y by x or cos theta z. So it depends on the zenith angle, that is the position of the sun in the sky with respect to the vertical. And we looked at different ways to calculate this air mass. One is using the zenith angle, one is using the length of the shadow of the pole based on the position of the sun. But both of these assumptions were made using Earth's atmosphere as a flat horizontal layer. But actually, to take into account the curvature, then there are some complicated, like mathematical correlations developed, which can also be used. But so far as 0 to 70 or 80 degree zenith angle is concerned, both of the approaches give the same value. So that's where we stopped, and then we took one numerical to apply the concepts of solar constant and air mass, and this will be used further, like whenever we have to calculate the radiations. If radiations are not given to us, the maximum possible value is solar constant and cannot exceed that for Earth. So with that, let's stop here, and we'll continue with the remaining part of solar energy in the next lecture. Thank you.